So I am based at the University of Lethbridge in Western Canada, and we were just recently rated by Maclean's magazine, which rates the universities in Canada as #2 for our undergraduate status. So we're very happy about that, and it's a great place. There's a map in the corner there if you're not sure where we are, right above the 49th parallel, about an hour and a half from the US border. And we're a university of about 10,000 students, so we're not a very large university, but we have a couple areas of niche expertise, and I've been lucky enough to stumble into one myself with the far infrared astrophysics, experimental astrophysics that happens. So this picture I took on my bike ride to campus a while ago, and we get wildlife and everything, and it's a beautiful place to be if you're ever in this neck of the woods. So I want to talk a bit about the far infrared. I'll go into Herschel and Spire, both European Space Agency telescopes launched in 2009. I'll talk a bit about a spectral feature catalog that myself and some of my students have been working on, and some other collaborators within ESA. And then a bit of time into the future of the far infrared. And on the right here are some spectral postcards from the Spire instrument, and some maps. So I'll go into more details on what those are in the talk itself. This plot is from Riley Hill, a UBC PhD student, a really interesting paper, The Spectrum of the Universe. Essentially, the point I want to draw here is that there's a lot of photons coming at us in the microwave background, microwave regime, and the far infrared, just a slightly higher frequency. And depending on how you measure, it's about half the photons incident on the Earth's atmosphere. Almost none of which can get through. So to see these, we need to go to space. So the Spitzer and Herschel have done great things from space, and also predecessor instruments leading up to them. ALMA in South America has done a lot from the ground through some narrow observing windows, atmospheric windows. And James Webb Space Telescope should launch soon and will again provide unprecedented data for astronomy and astrophysics. And all of the main science questions that are on the table right now in astronomy have areas where better resolution and better sensitivity in the far infrared will help us out. So this is just simply to illustrate how in the far infrared, so around 100 microns to 1 millimeter, nothing really gets through the atmosphere. So we have to go to space. Maybe on a balloon, maybe on the top of a mountain on a good day. But the real unfettered view is from a space-based observatory. I don't want to go into all the details here, but essentially drive the point that in the far infrared, stuff nearby within our own galaxy, dealing with star and planet formation, is a key area of exploration onto things in the nearby universe, galaxies that are nearby, and evolving universe, all the way back to the oldest light possible in the microwave background. We could learn more with more spatial resolution and spectral resolution or spectral sensitivity with the technology we deploy to do observations. And of course, the size of your telescope is a big limiting factor there with these long wavelengths. Just ripping through this, the main point here is if you have a bigger telescope, you have better spatial resolution. So this blue arc here, this circle is what shows up in a Spitzer Space Telescope image in 1 pixel. This is a simulated James Webb deep field, much like the Hubble deep field that I'm sure we're all familiar with. The Herschel telescope had a 3.5 meter diameter mirror. And so everything in this yellow circle is 1 galaxy, or sorry, 1 pixel. A goal is sub-arc second resolution at 100 microns, and that's kind of what the green square is here. And then the eventual long baseline space deployed interferometry gets us very high spatial resolution here. And again, everything in this image, all these dots and features are individual galaxies. So everything in those larger circles is integrated and then needs untangled through analysis and modeling and all sorts of complex things. If we could see it, it would just be that much better. So the background image is one taken by the Spire photometer on Herschel. And it shows Herschel and Planck together. The bottom left is Herschel, a 3.5 meter diameter mirror. and then cryogenic helium-cooled optics and instruments inside with a 3 to 5 year lifetime. It was launched in May 2009, and the cryogens expired in 2013. Planck was launched on the same rocket as Herschel. It's 1.5 meters across, not quite as big. It maps the whole sky. Herschel's an observatory with proposals and time allocation, and Planck just surveyed the whole sky. The Spire Consortium, Canada was actually led, the Canadian contribution was led through Lethbridge, and mostly European, but other partner agencies, including the US and NASA. So the Andromeda Galaxy, M31, we can see it with our naked eyes in the night sky. We see the central region of this galaxy. And if our eyes were more sensitive, or we have sensitive cameras to look at it, it's actually bigger than about 3 full moons in our sky. Here's what we see in the optical. Switching over to the Spitzer view of this source, you can clearly see the galactic center, and you can also see the spiral arms quite well. And what we're seeing here is light from young stars that have formed. So there's a lot happening at the galactic center, and there's also a lot of activity in the outer reaches of this galaxy. So equivalent to our Milky Way galaxy, we'd be kind of out 2/3 or so on one of the spiral arms if this was ours. Now, switching over to longer wavelengths with Herschel, here's what we see in Andromeda. Now, the central region is still there, but it's very faint. And these outer bands are the brightest element of this source. What we're actually seeing here is the clouds of gas and dust as things come together before stars are even formed. So we're seeing emission from interstellar material and molecular emission from clouds that are, say, 10 Kelvin up to maybe 100 Kelvin, minus 200, minus 250 Celsius. Here's another optical image of our full sky, and then I'm going to switch over to the Planck image, which is the microwave or far infrared image. Also give credit to Chris North at Cardiff University, chromoscope.net, if you want to play around with imaging the universe in different regions of the spectrum. That's a neat toy to play with. So across the center, you can see our galaxy, of course. It's very bright. There's a lot of stuff off the galactic plane that we're sensitive to and we see. And of course, the cosmologists that put Planck in the sky wanted to get rid of all this and see the microwave background. So in getting rid of all this foreground, you need to understand it quite well. And there's about a bunch of science there. Dipping back into history a bit, this is a painting of Herschel from the Royal Astronomical Society in Britain. And he was a musician. He was an organ player and a music teacher, and his sister Carolyn was an opera singer. And he found a textbook on how to make lenses and mirrors, and he played around and dabbled in astronomy as a hobby. And he went from that to become the world's one of the world's leading astronomers, and he was commissioned by King George to make the world's biggest telescopes at the time. In the foreground of this image is another experiment that Herschel did. He took sunlight and a prism, split it into its colors, and measured the various temperatures with a thermometer. He discovered past the red that there was still an increase, and these other thermometers are kind of a control, so just the room temperature. So Herschel, being a scientist or wearing a scientist's hat at this point, making measurements from a star, from an astronomical source in the infrared region of the spectrum. He was the very first infrared astronomer. And the detectors on Herschel and Planck are very much thermometers in some respect. So it being named Herschel is appropriate. It's not just taking pictures, there's also spectroscopy. So here's some spectra from the various calibration sources. I'll get into some of the spectroscopy a little later on as well. So Planck, a bit of history here. In the 60s, the Penzias and Wilson were struggling with some static in their radio antennas. They thought it was maybe bird poop or something. They cleaned it off and it got worse. So they eventually discovered that this static noise that was a nuisance actually was emission from the universe. So this egg-shaped circle is the map that was made shortly thereafter. Fast forwarding a bit to the COBE instrument in '92, which got John Mather the Nobel Prize. His PhD project was trying to do a similar measurement from a balloon, and it wasn't near as successful, but luckily they got things together and did that. Another decade later, this is Wmap. So these are the full sky images in the microwave region of our universe. And then Planck another decade later. And there's some updates to this, and I'll talk about some of them. But essentially, this was one of the first light images of Planck where we see our galaxy not being removed in the processing yet. And of course, getting rid of the foregrounds gets us to this Blackbody curve. So this plot here was from 1990. It's about 10 minutes of data, and it's a very beautiful Planck function. But there's more to it than that. So our cameras on our smartphone have 3 colors, red, green, and blue. Planck had 9 different colors. It was also polarization sensitive, so the same light that you use your 3D glasses with at the movies. There's information encoded in there in the universe signal. And the orbit was L2, so the second Lagrange point on the Sun-Earth system, about 10 times farther out than the Moon, but the orbital period is still a year, so we don't lose contact. So here is the sky seen through each of the 9 colors that Planck was sensitive to. You can see the galactic emission. It varies based on the color band in question. And this is helping all of the algorithms to remove the foregrounds and classify the information to get to the microwave background. There's also the various components that come out of it. One of the neat surprises with Planck was how much carbon monoxide was there. Its 100 gigahertz band was a little bit broader than the equivalent band on the Wmap NASA instrument. And in order to get to the cosmology, we now have a decent map of the carbon monoxide emission throughout the sky, which is removed as part of the data processing. So this is a temperature map of the microwave background. The difference between the bright reds and the dark blues is about 10 to the minus 5 degrees Kelvin. So kind of part per million signal density. And the distribution of these fluctuations in the signal, or anisotropies as they're called, tells you information about the early universe and what things were like back then. Now, to put this in context, if we take the same region of the sky and the same color scale, here's the image that COBE provided, Wmap, and Planck. So the slightly bigger telescope mirrors gets us more spatial resolution, and we can zoom in on what's happening. And to maybe put it in more colloquial terms, here's your Atari, your Nintendo, and your Xbox or PlayStation. And of course, the polarization signal. So this is temperature and polarization information superimposed, just illustrating that there's a lot to be seen. And a lot of that is to do with magnetic fields, and in our own galaxy and in nearby galaxies, certainly the magnetic fields have a lot to do with how star formation takes place. And well, this might look a bit familiar as well. So Van Gogh had some neat ideas as well. But to get into, so this plot is from the 2018 Planck data release, so the last data release out there. So there's Q and U, which are the 2 linear Stokes polarization parameters, and then the intensity on the right at all the different color bands. So just showing that there's a lot of information there, and a sort of smoothed all sky image is here. And I said the intensity information is about part per million. The cosmological polarization signal, where you find source for gravity waves or a confirmation of inflation, is about part per billion. So a lot of this information in this map here is actually foreground polarization. And here's zooming in on one of the spots, smooth so it can be seen. Several years ago, there was excitement from the BICEP2 team about finding evidence of cosmological gravitational waves. And there was a collaboration between BICEP2 and Planck where they pooled their data and their analysis and went looking. And unfortunately, the result was not that gravitational waves were dead, but more that it's a tricky measurement to make. So that needs follow-up and further study. But the dust and galactic foreground removal is an important part in this process. So on the right here, we have data from Planck, and we zoom in on the Aquila region just to emphasize, here's the resolution we had. Now, from prior instruments, it certainly does a better job, but comparing Planck's resolution with Herschel's, here's what we see in the same region. So there's some interplay with these two telescopes working together where follow-up work can be done. And zooming in there. Okay, I'm switching gears again to recent results. So the Herschel mission was from 2009 to 2013, so about 4 years. And the data that it produced in the far infrared, in many respects, was the first of its kind. Because we just didn't have access through the Earth's atmosphere. All of the data is publicly available, yet some of the instrumentation is a bit challenging to work through if you're not an expert in this type of equipment. And what we wanted to do on the Spire Instrument team is to make the data more accessible. So we developed some algorithms and processing routines to go through all of the spectra and hunt out spectral line features and make them publicly available, so you can search for spectral lines rather than just raw data. And that catalog is available through the Herschel Science Archive hosted by ESA. And there's 5 papers that have just come out in the last 4 months or so, going through and explaining what we've done. So I want to explain that in a little bit more detail. This table is from one of the papers. I want to highlight just in the upper right corner of the table, there's 2,000 hours of integration time with the Spire Spectrometer. And there's a lot of varied sources in there. So it's a Fourier spectrometer, which has a little bit interesting of a spectral line shape. This is a sync function or sign over argument. And if you could look through this black curve here from a sample source, calibration source, you'd see clearly there's a line here. And maybe you'd see this line here. But there's several others that once you start to peel the layers off, you can see better. So, and this is maybe challenging for somebody not familiar with the instrument. So there's 2 modes. There's sparse and mapping modes, and we provide postcards and data products for each. Here's a sample postcard from a sparse or a single pointing observation. The continuum spectrum, the sticks represent lines identified. The height is the signal to noise associated with them. And this is the array footprint for the detection bands, the 2 bands within Spire. There's also mapping mode. So postcards provided are intensity, integrated intensity, sample spectra, and then number of lines in the upper right, and then the radial velocity estimate. We've also looked at identifying not just where these lines are in terms of frequency, but the molecular or atomic source, and that is cataloged as well. And here's a histogram of all the distribution. There's a template we've used with over 300 spectral lines, but they mostly fall into these atoms and molecules. This is freely available. There's links here. And the archive AstroPH papers are all right here, freely available as well, or you can get them through the monthly notices of the Royal Astronomical Society. So this catalog provides just shy of 300,000 spectral features over the entire mission. And given that we don't know when the next far infrared mission is going to launch, this is the archival data set that we have access to worldwide, the best that is there. So within Canada, we go through the long-range planning, decadal planning process, as does United States and as does Europe. And in the far infrared, there's 2 main priorities. So there's spatial resolution.
You have 2 minutes to go, please.
Okay, great, thank you. So there's spatial resolution, so you can build a bigger telescope or have multiple telescopes in interferometry. And then there's aperture sensitivity. And so the Herschel mirror is 3.5 meters in diameter, and every photon from some astronomical target was accompanied by 1,000 photons from the mirror itself. So if you can cool that mirror down, Herschel's mirror was cooled to minus 200 about. If you can cool that much more, then you can chase your astronomical light instead of just stare at yourself. So SPIKA was a Japanese and European collaboration that was one of contenders for the M5 launch program within the ESA Cosmic Vision. Unfortunately, just 2 weeks ago or so, it was canceled, and that wasn't through the normal vetting procedures. So that is frustrating for some. Further information on that is available on this website, spikarebelalliance.com. There's an article in Nature Astronomy coming out very soon talking about some of these details as well. But SPIKA was basically next generation Herschel with a cooled mirror. And then there's interferometry. And you can do mechanically tethered formation flying different ways, but a series of space-borne Herschels or SPIKAs or NASA Origins instruments flying together to get that spatial resolution down. And that's on the long-term plan. In my lab, I'm developing a laboratory testbed instrument. There's some work in that front that's happening in NASA Goddard with David Leisowitz, who I see is present here as well. There's some groups in Europe and in Japan working on this a bit as well. And that's kind of where this will go in the future. So there's great data available right now. There's a legacy that's led us to this point historically, and there's technology development needed to get the science or to get the technology case ready when the next generation opportunity comes up. And it's been amazing to be part of this with my career thus far. So I thank you for your attention and the opportunity again. I apologize deeply for the technical glitches, and I'm happy to discuss this further and entertain questions.